This is lecture 7 on the topic of angular momentum. It's part of a mathematical physics course called Quantum Mechanics. It's at senior level, and the first author of the text I'm using is Davies, and here's the text called Quantum Mechanics, second edition, 2 authors, Paul Davies and David Betts. Okay. This is the text. Okay. Now, the previous lecture, 50 plus video clips, the longest lecture in the text, followed by this one, previous lecture, chapter 6, hence lecture 6, with many parts, each session given a letter. So this will be letter A, 7A, 7 for lecture 7, chapter 7. Now in lecture 6, chapter 6, I was referring quite a few times to this coming chapter, in other words this one, on angular momentum, because this chapter will show very clearly the power of the idea of using the Eigen Equation to generate new physics, new quantum physics. And you remember the basic idea of the Eigen Equation is that you have some operator that corresponds to some observable, and that observable's allowed, discrete, quantized values when you measure that observable. That idea of an Eigen Equation, so operator times an eigenfunction equals an eigenvalue, which is the allowed measured values you can obtain in a measurement of that observable, times eigenfunction. So operator, eigenfunction equals eigenvalue, eigenfunction. That idea is becoming increasingly important as we go through this text. And this chapter we will use that idea in the context of angular momentum, and then later, a bit later, spin. So you'll appreciate even more the importance of that idea of the Eigen Equation. All right. So a few lead-in comments. If your quantum system that you're talking about, for example, inner layers of electron layers of a hydrogen atom which are spherically symmetric, then you will get angular momentum conserved, because the Hamiltonian then is not a function, although the potential in V is not a function of the polar angles theta and phi, it's only a function of, say, the radius r, in which case V is independent of the polar angles phi and theta, and therefore that your Hamiltonian commutes with I think I better leave that. I had this problem last. I'll wait till the end of this this lecture until we got more theory under our belt. All right. So so we're trying. So if you're going to start on a new observable, and you now are motivated to apply an Eigen Equation to that new observable, so you need to find the appropriate operator corresponding to that observable, and that's the hard part, right? That's where the creative act comes in, because once you've got the operator, then finding the eigenvalues and the eigenfunctions, that's just part of solving the Eigen Equation, right? So the critical thing is finding the operator that you start with, because all the rest follows. So given now we're talking about angular momentum, how to go about finding the appropriate operator? Well, it's a bit of guesswork to some extent. You're guided by the correspondence principle, which formulated first by Bohr, Niels Bohr, and it's interpreted rather broadly, and it depends on the context. But basically it's sort of saying that quantum mechanics and classical mechanics can't be too far from each other. In appropriate limits, quantum mechanics needs to merge into classical mechanics, because classical mechanics works at our human scale, and quantum mechanics obviously works at the very tiny scale, the scale of molecules and atoms and smaller, and maybe even all the way down to strings, which is 10 to the minus 35 of a meter, if strings exist. Still rather hypothetical, untested theory at the moment. So in other words, you can get some guidance from classical physics to prompt you, to push you in certain directions in quantum mechanics. So you'll see here a case in point. So your question becomes, we're talking about angular momentum. So what would your angular momentum operator be for quantum mechanics that you could use for the start of solving an Eigen equation? Right? Well, so let's start with physics a bit and see what we can do. Now, a bit of it's guesswork, and you'll see that. And so, if you start with a guess, not a wild guess, I mean an informed guess, a kind of guesstimate, if you like, a guessing estimate. If and you can justify that, the guess that you make by its consequences. The results, the predictions coming out of the theory. The equation that you choose, the operator that you choose, if the results are good, then that would confirm your choice of your operator to start with. So, with that in mind, let's start. All right. So now, let's start with classical mechanics and get ideas, hints from classical mechanics, and see if we can convert them to some extent into quantum mechanical ideas. And the justification that, as I just said before, would be whether the results of these quantum mechanical analogies, if you like, are appropriate, are accurate, are reasonable. Okay, now here's the definition of angular momentum from classical physics. So it's just the cross product. Again, I assume you've done some vector calculus. It's not the dot product. So the cross product gives you, the result is a vector. So you take two vectors and cross product them, or the vector product, if you like, and the result is a vector. That's why I put a little hat under L. L is the usual symbol for angular momentum. Why is that? I don't know. It's a historical accent, I suppose. Maybe they ran out of letters. So the vector position, r across by the momentum. So you're talking angular momentum. So it's got something to do with momentum. So that's where your p comes in. The mass times the velocity. So, and why is this position coming in? Well, if you have a string and a weight attached to the string, and you're spinning this weight around, then the angular momentum will be more. Say it's rotating at a certain angular rate, right? So if the weight, say, miraculously doubles, then the angular momentum should be double, okay? And if the velocity, say then you suddenly double the length of the string, and this thing is still moving around at the same velocity, m times v, okay? But this length is now doubled, so the angular momentum, sort of intuitively you feel, should increase, right? Well, should double. Okay, so that's where the r comes in. So it's the length of the rotation, the radius of the rotation, if you like, times ordinary momentum, mass times velocity. So that's the classical version of angular momentum, right? Well, now we take a leap into quantum mechanics, we'll use this classical definition of angular momentum and try to find quantum mechanical equivalence, ENTS, the equivalent of the classical as a to guide us, right? So here's the main idea for that quantum mechanical leap. For the R and P term in your classical definition here, and keeping the cross product, right? Let's create an angular momentum operator, so quantum mechanical. So we'll put a hat over this L, and we'll put a hat over the R and a hat over the P. So in other words, you're taking the classical definition of angular momentum and just converting it into a quantum mechanical equivalent. Right? So you just put hats over these, and this is a vector. The right hand side is a vector. The left hand side is a vector. So let's say in three-dimensional space. So that means this right hand side will have an x component, a y component, and a z component. So you can talk about the x component of the angular momentum, L sub x, L sub y, L sub z. Okay?